So the final step with this binomial and geometric distribution are ways that we can summarize these distributions. So we're going to be able to calculate mean and standard deviation associated with these, and in doing so, as soon as we get a mean and a standard deviation, we're actually going to be able to, in some cases, use a mean and standard deviation to go into a normal distribution, and then we're also going to be able to do the same thing with geometric. However, we cannot take geometric into a normal situation. So this is what we've been doing so far. So here's another example. Suppose 75% of drivers wear their seatbelts. Find the probability model if there are 5 cars that we're interested in. So first, is it binomial? Right, we have 2 options. They either have their seatbelt or they don't. Um, each car independent. Sorry about the flashing. The probability they have their seatbelt on is 0.75, and we have a fixed number of trials, n equals 5. So it is binomial. So we'll go ahead and define our random variable as the number out of 5 who are wearing their seatbelt. So fill in the table. This isn't anything uh, tricky for us. Right here we can do binomial PDF, and so a trial of 5, probability of 0.75, that we get x equals 0, so on and so forth. Quick filling in the table now that we have that binomial PDF function in our calculator. And so once we're here again, what we've been able to do, what's the probability that 3 more than 3, right? So what's the probability that more than 3x is greater than 3? And we could try to use the binomial CDF if we wanted to, but the fact that we've already filled in the table, let's not do that. Let's just go right here. More than 3 would be 0.3955 plus 0.2373, 0.29, oh, excuse me, 3955 plus 0.2373. So about 63% of people will be wearing their seatbelts in those situations. Okay, so here's where it's going to be a little bit different to us. Finding the expected number of drivers that wear their seatbelts and find the standard deviation. Well, we've seen this before. We know how to do this. Easiest way to do this, right? Expected number. So the expected number of x, 0 times 0.00098 plus 1 times 0.0146, so on and so forth. Or we could go through and put list 1 and list 2, which is probably the easier way to do this, right? And using list 2 as a frequency list, we can run one var stats. And if you let me erase this, right here we would see, go ahead and plug that into your calculator. You'll find that the expected number of 5 drivers out of 5, so close to 4 drivers out of 5 will have their seatbelts on. And then standard deviation, that comes straight from that one var stats if you don't want to use the formula. But another way to go about this, if we know that it's binomial, so this is important, if we do know that it's binomial, there's a quick shortcut. The expected value, you could just multiply n times p, and then the standard deviation is the square root of n, so that's the number of trials, right? Number of trials. P, that's probability of success. And then this variable q, 1 minus p, well, really that's just the probability of, we'll call it a failure. Probability we don't have success. Excuse me. So go back to your previous scenario. Suppose 75% of drivers always wear their seatbelts out of 5. So the expected number would be 0.75 times 5, which is 3.75. The standard deviation, the square root, so n here is 5. The probability of success is 0.75. The probability they're not wearing their seatbelt is 0.25. And that number is 0.968. Well, what we saw on the previous page, so let me go back, were those exact numbers. So we can get to those numbers 2 different ways. It's just if we know that it's a random variable, if we know for sure that we have a, not just random, but a binomial situation, then we could go ahead and use that shortcut, these 2 shortcuts. So these are 2 great things to have jotted down in some notes. Uh, but again, that's only if we know it's binomial. So 8% of males are colorblind. A researcher needs some colorblind subjects for experiment, and so chooses a class with 200 students. So is it a binomial situation? That's the first thing. Just very quickly, there are two options. Either a student is colorblind or they're not colorblind. Each student is independent, right? One person being colorblind is not going to affect the next. We have a set number of trials, 200, and then the probability that someone is colorblind is 0.08. So we do have a binomial situation. Check. What's the probability that we find more than 20 subjects? So in other words, x is greater than 20. Now, with 200 students, I'm not going to make this table. This is a great opportunity to use my binomial. And since we're doing an inequality, it's going to be CDF. So it's 200 students with a probability of 0.08. But the trick here, remember, this binomial always does less than or equal to. So we need to turn this into something that is less than or equal to. So what we saw yesterday, this is actually the same as 1 minus the probability that x is less than or equal to 20. So we can do 1 minus the binomial CDF. So binomial CDF out of 200 trials. So the probability that we find more than 20 test subjects in that big class is about 12%. So it's not extremely likely that they're going to get a bunch of subjects that they need. So how many might they be able to expect to find? In other words, what would be the average number of colorblind people in that class? So what we can do here, the average number would be n times p. So for us, we've got 200 students times 0.08. So basically, it's 8% of 200, which is 16 students. Now, that's not going to be the exact number, so we could take a look at what would we expect the standard deviation to be. So for us, that's the square root of 200 times 0.08, and then 0.92. And we take, okay. So we would expect some variation from class to class. So 3.8 students. So typically we probably find between 16 to 19, maybe 16 minus, so about 12 to 20 students in a class that size that might be colorblind. So we can actually take some of these into a normal situation. So if we have a big sample size, we've got to have a very big sample size, typically. So what needs to happen, n times p has to be greater than or equal to 10, n times q has to be greater than or equal to 10. So how does it then become normal? Well, remember for a normal calculation, right, to do z we need some critical value minus a mean over a standard deviation. Well, we just saw that the mean is going to be n times p, and the standard deviation is the square root of npq. So if we have a binomial situation, if it's binomial, and these two conditions, np is greater than or equal to 10 and q is greater than or equal to 10, then we have a normal distribution, and our new mean is n times p, and our new standard deviation is npq. So how would that work for us up here? Let's look at the previous example again. We've already seen this is binomial, so can we use a normal approximation? So before we can move on, we need to check NP and NQ. So NP is 200 times 0.08, which we saw was 16, and that's greater than or equal to 10. That works. And then 200 times 0.92 equals 184, which is also greater than or equal to 10. So NP is greater than or equal to 10, and Q is greater than or equal to 10, which means we can now use a normal distribution. So what's the probability x is greater than 20? Well, we can now get a z-score. Our critical value here, right, is 20. our mean from before. Remember, the mean was n times p was 16, and our standard deviation, square root of 200 times 0.08 times 0.92, that was 3.84. So our critical value minus 16 over 3.84. So our z-score here, 1.04. So we're just above one standard deviation. We don't have a probability yet, but since we know we can use a normal distribution, right, we're going greater than or equal to 20. So for us, remember our mean was 16. So just a quick shading here. We're just over one standard deviation above. So our critical value again was 20. So our lower bound is 20. Our upper bound is infinity. Our mean is 16. Standard deviation is 3.84. So the probability that we get more than 20 students, go to that normal distribution. Mean is 20. Standard deviation of 3.84. Very 0.149. So about 14% of the time he'll get his 20 students, that particular researcher. We can look at it one more time here. So another quick example. 60% of adults have credit card debt. So is it binomial? One, there's two options. They either have debt or they don't have debt. Each person is independent. Notice that I'm going through this every time. The probability that they have debt is 0.6. And if we survey 2,500 adults, so we have a set number of trials. Is it binomial? Yes, I just went through that. Can we make it normal? So NP and NQ. So 2,500 times 0.6, 2,500 times 0.4. These are both greater than or equal to 10. So can we make it normal? Yes. So how is it normal? Well, we need a mean, which would be n times p, 2,500 times 0.6. 2,500 times 0.6, excuse me, is 1,500. And then a standard deviation is square root of 2,500 times 0.6 times 0.4, which is 24.49. And so what we need to do is write a probability statement, probability that more than x greater than 1520. So we now have a critical value as well. So 1520 minus my mean of 1500 over 24.49. Right. So 1520 minus 1500 over 24.49, 0.817. And then so our normal, since we know that we're allowed to do a normal, my lower bound here, so the sketch might help very quickly. So my mean was 1500. I wanted 1520, which wasn't quite one standard deviation, and everything up. So my lower bound here is 1520. My upper bound is infinity. Let me clean that up just a little bit. My upper bound is infinity. My mean was 1500. Standard deviation 24.49. So normal CDF from 1520 to infinity. The mean of 1500. That probability is, so the probability here is 0.21. So about 21% of the time we'll run into 1,520 or more in a sample of 2,500 adults. So the other way to do this, so this is formulas for a geometric setting. The expected value would be 1 over p, And the standard deviation would be Q over P squared. This doesn't happen a lot. You don't see this a lot, but um, if we go back to our Hawaiian, keeping in mind, right, the proportion that somebody was Hawaiian from the problems we've been doing was zero.8. So the way this question could go, what's the average number of villagers it will take until we meet the Hawaiian? So that would be the expected value. Right, again, this is an expected value. So with 80% of the people, you plug in. Um, so there's expected value, there's standard deviation. So it take just over one villager. Typically, with so many native Hawaiians, you would expect to meet most of them. And then how much variability? It's literally just plugging into the formula. Again, Q, that's just 1 minus P, or the probability that there's failure. So 20% of the people aren't. Plugging into the formula is pretty straightforward. I'm not going to do all the problems here. So here's the sales call, and we've done it before. And we've done stuff like A, B, and C before where, you know, this is a geometric setting, right? The probability that your first sales call, right? So is it geometric? Sure, there's two options, right? You make a sale or you don't make a sale. Two, each call is independent. Three, the probability that you make a sale is 0.19. And now we're going until success. Um, so number of calls until first sales, it is geometric. So here for part A, you're doing the probability that x equals 5. So that would be geometric PDF, or a particular value. Right? So the probability, and you make on the fifth call. For part B, you make your first sales call on the first, second, or third. So that's probability x is less than or equal to 3. Well, that's geometric CDF, 0.193. Part C, you do not make a sales call on the first 3 calls. So that's probability that x is greater than 3. Well, we got to play the trick again. So this would be 1 minus the probability that x is less than or equal to 3. And so we do 1 minus geometric PDF, excuse me, CDF, geometric CDF, because it's continuous, 0.19, comma 3. That's how we get those values. That's not new. The new type of question, so how many calls would we expect to make until we get our first sale? So for part D, so the expected number of calls until a sale, remember, so if we go back to our formula, 1 over P, so 1 over our probability of 0.19, so we would expect to make about 5.26 calls. Think about it. If you're having success 20% of the time, we would expect about 1/5 of the calls to be successful. So you'd expect to have to make 5 calls before you make your first sale. And just so we can see it, the standard deviation associated with this, again, there's your formula. So that's the square root of Q over P squared. So for us, Q was 0.81, 0.19 squared. So 0.81 over 0.19 squared. And then take the square root of that. So the standard deviation associated with this, 4.74 calls. So in other words, we would typically expect within 1 or 2 standard deviation, that plus or minus 1 standard deviation. So between 1 and 9 calls, we would definitely expect to make our first sale.